Good evening. I'm Kelly Otter, the Dean of the School of Continuing Studies here at Georgetown University. And it's my privilege to welcome you all here this evening. This is our downtown campus at 640 here, the School of Continuing Studies. And it's my honor to be here and welcome our distinguished guest, Dr. Vint Cerf, and to celebrate the great work of the National Science and Technology Medals Foundation. We have a few special guests joining us this evening. Thank you to Mr. Andre Iancu, Undersecretary of Commerce for Intellectual Property and Director of the United States Patent and Trademark Office. Likewise, I'd like to offer a warm welcome to Mr. Andrew Rothman-Noonan, Executive Director of the National Science and Technology Medals Foundation. Thank you for bringing this event to life. The mission of the Foundation, to champion the work and lives of Americans' greatest scientists, is a noble charge that we at Georgetown are very proud to support. As an educational institution, unfettered pursuit of the truth in the science and humanities is the core of our mission. We have educated students and facilitated research in the service of the public good for almost 230 years. Like Georgetown, the Foundation is committed to inspiring the leaders of tomorrow to pursue excellence. This work involves finding ways to connect the greats of science and technology to the next generation of innovators through events like this one that we're holding this evening. And one of the true joys of my job as Dean is when we find key moments to host these very important conversations. As we prepare our students to succeed in industries and economies that are constantly evolving and changing, hearing from esteemed leaders in these diverse fields enriches our students' educational experiences and enlivens the academic discourse on campus. Thank you, Dr. Cerf, for contributing to this mission. You have my best wishes for an enjoyable and edifying evening, and thank you for joining us in this important conversation. And I would like to welcome Director Iancu to say a few words.
Thank you, Dean. Very, very kind of you, and thank you for hosting this wonderful event. So in 1980, the United States Congress passed legislation directing the President of the United States to recognize America's greatest technologists and innovators with the nation's highest award for achievement for their groundbreaking accomplishments. Since that time, over 220 men and women, corporations, and nonprofits have been honored by the President at the White House ceremony to receive the National Medal of Technology and Innovation. Our sister award, the National Medal of Science, administered by the National Science Foundation, was first presented by President Kennedy in 1963. Over 500 renowned scientists and engineers have received this prestigious award over the past 55 years. The United States Patent and Trademark Office is very proud to be a part and to play the administering role in the National Medal of Technology and Innovation on behalf of the Secretary of Commerce and the President of the United States. With nearly 13,000 employees and a mission to grant patents and register trademarks, and to lead the nation's dialogue on innovation, we at the USPTO believe we're uniquely qualified and positioned to spearhead this important project. In fact, we look forward to granting the 10 millionth patent later this summer. A milestone for the USPTO and an important milestone for this country. Think about that. 10 million patents from the foundation of the country. No other nation in history has accomplished that, and we will get there probably in mid-June or thereabouts. As you can tell, we are honored to be at the cutting edge of the nation's technological progress and achievement, protecting new ideas and investments in innovation and creativity. We are also very proud of our partnership with the National Medal Foundation and the exceptional work they're doing to honor and highlight the remarkable laureates who have contributed so much to our country and to all of humanity. We are especially privileged to sponsor the Foundation An Evening With series and look forward to working closely with Andy and to make this program even more effective in bringing the amazing stories of laureates to audiences like this. One of those laureates is our guest speaker tonight, Vint Cerf. Andy Rothman-Noonan will give a fuller introduction of Dr. Cerf, but I can't resist. I'd like to highlight what I believe are a few indispensable and vital traits of great innovators. To keep thinking, to keep tinkering, to keep pushing us ahead to a better future. After Thomas Edison invented the phonograph, the speaking machine, in what year, Dr. Cerf? 1877. A major magazine of the time said this of Edison: with his inventions, he pushes the whole world ahead to the highest civilization. And that is what great innovators do. And Vint Cerf certainly exemplifies the brilliance and perseverance of a great innovator. He could rest on his laurels and accomplishments. After all, being known as one of the fathers of the internet is a pretty significant legacy. And some might say, good enough. But Dr. Cerf is not looking back, and he's not resting, he's looking to the future. And the future is filled with all sorts of unimaginable things. Digital data, for example. Data from 20 years ago. Data from this morning. Data that's happening and recorded now. And data long into our futures. Dr. Cerf is asking if that mass of digital data means a bright future, or perhaps something else. He's working on solutions to preserve our digital history, for example, working on the threats to eradicate our history, and the important stories that the future needs to know to thrive and flourish. It's this desire to solve difficult problems that drives great innovators and leads to innovation and discoveries that make all of our lives better and more fruitful. We need innovators and inventors like Dr. Cerf. I hope that you will discuss, Dr. Cerf, some of this more tonight in your interview. I am betting that the kinds of things you will be discussing and the kinds of solutions that you will be discovering will one day still come to our patent office, and we will have the privilege to issue you some more patents for more breakthrough discoveries. Hopefully you apply for them. I urge all of you to come meet Dr. Cerf, speak with him, ask him what he does and why he does it and why he did it and how he did it, and try to see what it takes to be like him. That is the purpose of evenings like this. In the meantime, it is my privilege to welcome Andy Rothman-Noonan, Executive Director of the National Metals Foundation, and he will tell you more about our esteemed guest. Thank you.
All right, well, I'm Andy. It's great to see all of you here. Thanks a lot for coming. As you've heard, I'm the Executive Director of the National Science and Technology Metals Foundation. We're both incredibly pleased and humbled to be hosting this event here at Georgetown School of Continuing Studies. Last year, we hosted our first Evening With event featuring the very guest you're going to hear from tonight. He was kind enough to carve some time out of his very busy schedule to take a leap of faith with us last year, and we're incredibly grateful that he did. I'll have you guys all know our Evening With program has now grown into an 8-event series held at academic institutions all over the country. We have big plans for it in the years to come. As Director Iancu mentioned, the goal of each of our events is to provide an audience like all of you the opportunity to access the greatest minds in science and technology, the laureates of the National Medal of Science and National Medal of Technology and Innovation. These women and men have accomplished truly great and world-changing things. We want to share their awe-inspiring work, but we also want you to understand who these people are as individuals. Individuals who experienced both failure and success, just like every single one of us. Without a doubt, the laureates of the National Medal of Science and National Medal of Technology and Innovation are a collection of people who have captured the power of scientific and technological progress, saved lives, engaged millions, and inspired us to exceed beyond the boundaries of human capacity. With that in mind, and before we invite our guests on stage, I always like to do this, get people moving. We're going to play a little bit of a game. It's Thursday. It's almost Friday. This will get you guys the juices flowing. So it's a very simple game. I'm just going to ask a question, and you all are going to raise your hand if it applies to you. Who here is a current student or an alumni of Georgetown? Great. Good showing. Whew. All right. National Medal of Technology Innovation Laureate Mark Humayun is a fellow Georgetown alum. He invented the Argus II. It's a revolutionary tool that allows patients who were once blind to see again. Who here has taken a course in software development or software architecture? Mary Shaw is a National Medal of Technology and Innovation Laureate who's responsible for creating the entire field of software architecture. Without her, we don't have the basic operating building blocks to be able to create devices like anti-lock brakes or, I guess more importantly, viral videos. That's a joke. We're here for, who's here of cryptography? Who's here heard of cryptography? How about cybersecurity? Good, everyone. All right, National Medal of Science Laureate Solomon Golom developed something called nonlinear shift registers, which are the basis for cryptography and cybersecurity. And finally, who's heard of the internet? Good, we've finally got everyone's hand up. Good, all right. Well, you're going to hear from the co-founder and architect of the internet tonight. His name's Dr. Vint Cerf, as we've mentioned before, and he's currently the Chief Internet Evangelist at Google, which, in my opinion, might be the coolest job title out there. He's a member of the National Academy of Engineering and a recipient of the Turing Award, the Presidential Medal of Freedom, and the National Medal of Technology and Innovation. I've actually come to know Dr. Cerf quite well over the past few years because he volunteers his time as a member of our foundation's board of directors. And I've come to appreciate his incredible knack at taking a very complex idea and breaking it down in a way that is readily understandable. Too often, we fear the things we don't understand, and we have people like Vint who can take us by the hand and show us that technological progress can be a powerful agent for positive change. Leading our conversation tonight is Brian Fung of the Washington Post. We're also thrilled to have him here as well. Brian covers technology at the Post, focusing on telecommunications, internet access, and the shifting media economy. So with that, I'd like to welcome Dr. Vint Cerf and Brian Fung to the stage. Thanks.
Vint, thanks so much for joining me tonight.
Well, it's always a pleasure to talk to you, Brian. And before you even ask the first question, I want to compliment you and your colleagues at the Washington Post. It feels to me like it has been invigorated by its acquisition by Jeff Bezos. I've been in this town for 42 years, and I'm seeing a wonderful and I would say incredibly investigative, powerful force here in the Washington area. You're part of that, and I really appreciate it.
Well,
I've told Jeff the same thing, so there's no secret here. It's just nice to see. Look, journalism has been in a really tough situation with the economics of journalism changing so dramatically, with the basic business model sort of disappearing, advertising primarily. And so it's nice to see that someone has put a lot of effort into essentially revitalizing a very important function in our society.
Well, we're also being sustained by our readers who we couldn't do without, and we're seeing a lot more interest in people reading our work these days, and it's been really gratifying to see that happen.
I can tell you, my wife doesn't allow any dead trees in the house, so we're subscribers to your online version.
Well, that actually leads into my first question, which is, we're going to get to the heavy stuff, obviously, but I'm personally very curious about, what your internet habits look like, how you use the internet, what kind of services you can't do without. Do you use ride sharing? Are you on Facebook? How do you use the internet?
Well, I have to confess, I have discovered that I can't even write anymore without being online. I mean, in fact, there was a power outage once, and so I thought, oh, well, I got out a pad of paper and I started writing. And I stopped about halfway through the first sentence because I needed to look something up. And there wasn't any Google available because the internet was down. And I finally just put it down because I couldn't make myself go on without getting the answer to this, when did this happen, or who did that, or who said what. So I'm online a lot, and I use our product at Google constantly. So that's one obvious thing. I use it for online purchases, for scheduling travel, open table for restaurants, streaming video, Netflix, YouTube. And I sort of didn't pay too much attention to YouTube, to be honest. I thought, well, it's probably got a lot of cat videos and it's for the kids. I'm not interested in that. And I was told young people are turning to YouTube more than they turn to Google to look things up. And I thought, oh, that's weird. Until one weekend, my wife and I decided that we would try to figure out how to make Chinese eggplant. With the long, skinny Chinese
well, I could
eggplant
taught you that.
That's really, well, you were out of town at the time. So I thought, well, why don't I try this thing out? Because the kids always go there for how do I? So I said, how do I make Chinese eggplant? We must have gotten 20 or 30 videos. And so we sat there and we watched them. And then we ran out and we bought some Chinese eggplant. We bought some of the Chinese pepper, that kind of weird red stuff. It does funny things to your senses. Anyway,
Does it make your mouth tingle a little?
Yeah, it's like a metallic thing. So anyway, we successfully made Chinese eggplant. So I came away with a better appreciation for why people would go to YouTube, because often if you're trying to figure out how to do something, somebody's already done a video to show you how to do it. So that's actually pretty cool.
So now I'm expecting to get to sample your recipe now.
Okay. We'll invite you over, and you can tell us whether we got it right.
Tell me the story of how you actually invented the internet. A lot of people know you as sort of the father of the internet.
I'm not the only father. Let's make
a co-inventor of the internet.
Yes, thank you.
How exactly did that happen? Tell us that story.
It's like, did I have a bad trip or something? This is... my partner, Bob Kahn, and I had both worked together on something called the ARPANET. We were not the only parties working on it. None of these big things happen with just one or two people. It's not like Edison back in the lab. It's collaborative work. In fact, if you want to read a good book on collaboration and invention and everything, The Innovators by Walter Isaacson is a good exploration of this partnership thing. So anyway, Bob was one of the key designers of something called the ARPANET. He was working on the packet switches that built the core of the system. And he was at a company called Bolt, Beranek, and Newman in Cambridge, Massachusetts, and they were operating under a contract to the Defense Advanced Research Projects Agency, which is an organization that got started back in 1958, just after the Sputnik launch by the Russians, and it caused everybody to go, yeah, how did that happen? And let's not let that happen again. So Bob was one of the key designers. I was at UCLA as a graduate student at the time, studying computer science, and ended up in the laboratory of Len Kleinrock, who had developed the mathematical theory behind packet switching using queuing theory. So he'd been analyzing theoretically what the performance of a packet switch net would be, and now we got an opportunity to actually build one. So the Network Measurement Center was at UCLA. We received the first node there. And after we got 4 nodes up and running of the ARPANET around the end of 1970, Bob shows up at UCLA and he says, I think that there are bugs and problems in the design of the detailed routing protocols, but my colleagues don't believe me, and I think it's going to end up, jamming up in some places. So my job as the principal programmer for the Network Measurement Center was to write software to force the network into some, overloaded state so that Bob could go back to his colleagues and say, see, it broke. We have to fix it. So we partnered for about a month doing these tests, and we would knock the network down regularly. And I almost got to the point where I wanted a rubber stamp with a little network thing on it that I could stamp on the side of the computer every time we broke the network. Kind of like the things you stick on an airplane if you shot somebody down. So we didn't do that, but that was tempting. So anyway, so Bob goes off back to Bolt, Beranek, and Newman, and then in late '72. He joins DARPA. And I leave UCLA and I go to Stanford to join the faculty. And in the spring of '73, Bob shows up in my office, in the lab at Stanford. And he says, we have a problem. And what do you mean, we? And he says, well, This ARPANET thing really worked well. We had invented, not Bob and me, but Ray Tomlinson had invented electronic mail around 1971. And everybody loved it because it was a computer-mediated thing. You didn't both have to be awake at the same time to communicate. You could just send a message and then respond it whenever you were awake. So we really liked that. And then the first two distribution lists that were invented for email were obviously social media, right? One of them was called Sci-Fi Lovers. And it was arguments among all the geeks about who were the best science fiction writers or stories. And the other one that I remember was Yum Yum. It was a restaurant review that Stanford was doing for restaurants in the Palo Alto area. So right away, within a few weeks of the arrival of electronic mail, we're seeing it is emerging as a social medium. So we had a clue that there were social functions that this network could perform. But then the Defense Department said, you know, computers are really powerful tools. What if we could use them in command and control? What if we could use a computer to help manage our resources that might allow us to take a smaller force and manage it better than a bigger force? That's a force multiplier. You might overcome a larger opponent.
And so this wasn't just for things like missiles, it was for things like tanks and stuff.
Well, the motivation for the Defense Department was, how do I use computers in command and control? Mm-hmm. The rest of us are using the network for a variety of other things. And mostly we're in the research world, so we're using it to exchange software and to get access to time-shared machines remotely and to exchange email, coordinate research, and things like that. So we could see a lot of civilian applications. The Defense Department, of course, is saying, we invested in this thing. What can we do with it? So Bob shows up and says, well, we're looking at the possibility of using the internet or the ARPANET, or computers anyway, in command and control. And he said, but there's a problem. We built the ARPANET out of dedicated telephone lines connecting the packet switches to each other. But if you're going to put computers in ships at sea and in airplanes and mobile vehicles, you can't use wires to connect them. The planes will never make it off the tarmac, and the tanks run over the wires and they break, and the ships get all tangled up. So we had to develop, or Bob started work on a packet satellite system using Intelsat 4A over the Atlantic, and a mobile packet radio system, which was put up based on radios built in Collins Radio in Texas, but we set up the mobile radio system in the Bay Area near San Francisco. So we had these three networks. So Bob's saying, you know, we have these three packet switch nets. The satellite thing has high delay because it's going all the way up to synchronous, and it's got packets of a certain size, and the data rate is a certain speed. The mobile radio system is lossy because the mobile vehicles are moving around. They come under a bridge and they're in radio shadow, and then they come back out again. So we have a lossy system with different packet sizes, packet error rates, and then we have the ARPANET. So he said, how are we going to make it look uniform? How can we possibly get all these different kinds of packet switch nets to look the same from the standpoint of any computer connected to any of them? And how can we make sure that any computer on any of the networks can refer to and get connected to any computer on any other net? And oh, by the way, we want this to continue to grow, so we don't care how many nets there are. How do we build this so it's just ultimately scalable? So we worked for about 6 months together. He would come out to Stanford, or I'd fly back here to Washington. And in 6 months, we figured out roughly how to do this. So we wrote. And
what was the biggest challenge in that 6 months?
Well, first of all, we had to figure out what were the ground rules. You know, how to frame the question. Everyone in this room must know that how you ask the question is often the key to finding the answer. If you don't ask the question the right way, you may never find the answer. So the first thing we agreed is that we would not change the networks in order to make them know that they were part of the internet. They had to be completely ignorant of the internet because they already existed. And they all have their optimized ways of doing things, none of which knew anything about the net. Each network thought it was the only network in the whole world. So we had to invent an addressing scheme that would allow a computer on any one network to refer to a computer on some other network somewhere in the world. Then, so that led us to design an internet addressing structure that had basically network identifier and a host number, a host identifier. And ironically, well, this is 1973, and we're trying to figure out, okay, so how many possible terminations should we plan for in this system? Remember, it had to be global because the Defense Department has to operate all over the world. And we also ruled out the use of country codes. Unlike the telephone system, which has country codes associated with each country's telephone system, we said, no, we don't want to do that. And we reasoned our way into this. We knew that the military would have to operate anywhere in the world. We also knew that if you were planning to invade country B, you couldn't very well go to country B 2 weeks before that and say, could we get some address space from you? Because we're planning to invade you in a couple of weeks and our command and control system won't work unless we have, you know, that was a non-starter. So we said, this system has to have essentially addressing structures which are independent of any geographic or national region. Not only that.
Before you go any further, how many endpoints did you initially?
Well, I was going to tell you so we were sitting, we knew that it had to be global. So we said, okay, first of all, how many networks will there be per country? And we guessed 2, so there'd be some competition. And then we said, and then well, we had just finished building the ARPANET, and that was a national scale system, and it wasn't exactly inexpensive to do that. So, so we had 2. And then we said, okay, how many countries are there? And there wasn't any Google to ask back in '73. So we guessed at 128 because that's a power of 2. And that's what programmers think in. So, okay, so 2 times 128 is 256. That's 8 bits. So we had 8 bits of network address. And then we said, how many computers per network? And we thought, go for broke, 16 million. Now remember, this is 1973. Computers are giant machines that are hiding in air-conditioned rooms, and they don't get up and wander around, and they don't fit in your pocket. But 16 million is 24 bits, and so 8 plus 24 is 32 bits. That was a nice round number. It was really great for computers of the day. So that's 4.3 billion terminations, which is more people than there were in the world at that time in 1973. So we thought that's surely enough to do an experiment. And it was, and that was a perfectly reasonable number. There were more than 256 networks ultimately, so we had to adjust the addressing structure to take account of the fact there were more networks than we expected. But we didn't actually run out of that address space until 2011. So it almost lasted 40 years, conceptually anyway. We did realize, though, that this was going to be a problem. So about 1992, a bunch of us were working in the Internet Engineering Task Force and developed a new addressing structure called IP version 6 instead of the 32-bit IP version 4, which gives you a clue. We went through 4 iterations of the initial design before we froze it and then released it in 1983. So IP version 6 has 128 bits of address space. If you do the math, that's 3.4 times 10 to the 38th addresses. That's a number only the Congress can appreciate. And I used to go around saying, man, that means every electron in the universe can have its own web page. Until somebody sent me a note from Caltech, dear Dr. Cerf, you jerk, there's 10 to the 88th electrons in the universe, and you're off by 50 orders of magnitude. So I don't say that anymore. But 10 to the 38th is a lot of addresses, so I hope it lasts until after I'm dead. Then it's somebody else's problem. So we are now in the process of shifting the internet over to run V4 and V6 addresses in parallel. It's about 30%, 35% penetrated around the world. And we're working to get the rest of it up and running. So I know we're wandering all over the landscape here, but the hardest problems had to do with the addressing question. How do I make a global address space? It's not country dependent or geographically dependent. And then we had to figure out, what should this internet protocol do? The protocols that had been designed for the ARPANET assumed that the underlying network was reliable. And there was a lot of work done by Bolt, Beranek, and Newman to make it so. But when we introduced satellite and radio, we realized, and then of course Ethernet came along, by the way, in May of '73 at Xerox PARC, which is a mile and a half from my lab at Stanford. This was Bob Metcalf and Dave Boggs. In May of '73, just as Bob and I are starting to do the internet design in the first place. So that was also a potentially lossy medium. So we realized at that point that we had to have a highly reliable end-to-end protocol between the host computers, that we couldn't rely on the intervening networks to be reliable. And so we had to build end-to-end retransmission, duplicate detection, reordering if things got out of order. That's what TCP was, Transmission Control Protocol. And so we designed that to be highly reliable. And so we had, that was a primary problem to figure out. There was another thing that was very interesting because as the development unfolded around 1977 or so, a number of people said, you know, this really reliable end-to-end protocol is not going to do everything that the Defense Department needs. He said, what do you mean? He says, well, it may be reliable, but every time you retransmit something, there's delay associated with the end-to-end transmission of whatever it is you're sending. And that for real-time traffic, retransmission is probably the wrong thing to do. For example, if it's a missile that you're trying to track, retransmitting the data about where it was is of far less interest than where is it now. And so you don't mind if you lose data as long as you get the latest data in the case of radar. The same is true for voice and video. You don't mind losing a packet. You might hear a click or a pop, or you have to say, please repeat that. But you don't want delay in the voice communication. If you've ever done a satellite call, and you know you start talking over each other because of the long long delay up and down. So we said we have to make these low latency protocols. So we split off the internet protocol from TCP, and hence the name TCP/IP. So IP is the real-time protocol, which doesn't guarantee delivery, doesn't guarantee keeping things in order, but it guarantees that we'll try to get there as quickly as possible. So we split those two off in 1977. The internet protocol layer is really interesting because it's illustrative of core principles in the internet. So the first interesting thing about the internet protocol layer is that the packets that are in the layer don't know how they're being carried. Think of them as postcards for a minute. A postcard doesn't actually know whether it's going in a car, an airplane, a train, or the back of a bicycle, and it doesn't care. The postcard doesn't care how it got carried. And that's true of internet packets. They have absolutely no clue what the medium is that is carrying them, which meant every time a new communication medium came along, we could sweep it in and put it underneath the internet layer of protocol, because the internet layer didn't care. Then if you go to the other side, you look at above this, you look at the internet protocol layer, and that layer doesn't know what it's carrying, just like a postcard doesn't know what you wrote on it. And the reason that's important is that because the packets are not knowledgeable about the meaning of the bits they're carrying, then the applications are only understood at the next layer up, at the edges of the network. So if you invent a new application, you don't have to change the underlying internet, you just have to change the interpretation of the bits that are flowing around in the packets. So this gave rise to a paper written by a guy whose name I'm not remembering now, but it was called The Rise of the Stupid Network, because it didn't know these things, and it made it very flexible. When people invented new applications, we didn't have to change the net at all. We just changed the software at the edges. So getting that right, getting these architectural pieces right in order to allow for lots and lots of innovation was part of the key. If you actually read the Internet Protocol specification, no normal human would do that, but if you did, you discover there is not one word in there about routing. Not one word. There's nothing, even though that's the core of the system, which is to take a packet from the host and route it through the network to get it to go out the other side. But we weren't sure how we were going to do that. So we specified the basic end-to-end protocol, and then we said, and then somehow or other, routing happens. It's like that cartoon where there's a bunch of math, and then there's a blank spot, and then there's some more math, and in the middle it says, and then a miracle happens. So that's sort of what routing was about. We ended up trying out a whole bunch of different routing protocols, and because we didn't incorporate that into the IP layer as a specification, it allowed us to go try a whole bunch of different things out. So the routing system simply received the packet and then looked in a table which was created somehow by some routing algorithm to say, this is going to that place, where should I send it? And it says, send it out that link over here. So these sorts of things were just key to the architecture.
Vint, if you were to go back and do it all over again, what would you do differently?
Oh, I thought you were going to say, what is that great saying, if I had it to do all over again, I'd do it all over again. Right, yeah. So two things. First of all, I would have chosen the larger address space so we didn't have to go through this IPv4 to IPv6. But, you know, it wouldn't have been credible. Can you imagine, you know, saying, okay, we haven't even built this thing yet. Here's the spec, and I need 3.4 times 10 to the 38th addresses to do an experiment. You know, it doesn't pass the red face test. But if I could have convinced myself, let alone anybody else, that would avoid this painful transition. The other thing is that cryptography has become very important. We saw all the hands go up. But at the time, the only form of cryptography that was available was called link encryption, which basically meant continuously encrypting the data that was flowing on the link. And it's a point-to-point thing. But we've got packets going in different paths through the network, and we needed to encrypt each packet independently because it doesn't go on a particular path. It could go on any path. So we had to be able to encrypt and decrypt the packets independently, even if they came out of order. So we developed packet cryptography while I was still in the Defense Department managing the program for DARPA. That was part of our major development, was a packet crypto capability. The trouble is that the equipment that was used at the time, we're talking 1975 or so, was classified. So I couldn't tell most of the people who were working on the internet exactly how the cryptography part worked because it was classified. In the meantime, my two colleagues at Stanford, Whit Diffie and Marty Hellman, invented public key crypto. They published a paper in 1976 or 77. I was here at DARPA at the time. It's arriving just as we have sort of finalized the TCP/IP structure. They announced this interesting possibility of two-factor, cryptography, but they didn't offer a protocol or an algorithm, so I couldn't do anything with it, even though it was very intriguing. And the next year, when I think RSA pops up in 78 or 79, finally there's a thing you could actually do. Except I have, as the program manager, decided to freeze the effort and start implementing it so I could deploy it and see if it would work. So we didn't try to do the crypto for the public key crypto for the internet in 78. And I have this feeling, looking back, that if we had, we might have had a more secure network. But it's not clear that the people who were using it at the time, which was mostly graduate students, would be reliable users of crypto keys and everything else. I mean, so it's not clear to me whether adding that burden of discipline and use would have helped. So, because most people didn't think that this packet switching thing would actually work at all, especially the traditional telecom people who use circuit switching as a way of communicating. So the hard part, there were technically hard parts, but there were also the problem of selling people on the idea that this might actually work. So my experience is reflected in what I tell my engineers, which is that the first thing you need to learn how to do is sell your ideas. You have to have some ideas to sell, obviously, but if you don't know how to sell your ideas, then you can't get people fired up to want to do what you want to do. So that's a really important skill to have, and I can assure you that over the period from 1973 to the present, that I've always felt that that was an important role to play in innovation, was to help people get over the how could that possibly work feeling, or I don't want to do anything different because that's a change and I don't want to change. So learning how to sell, how to get a lot of people excited about the possibilities is part of making things happen. So even though we use words like scientists and everything else, look, I'm just an engineer who wants to make stuff work. That's the thing. Solve problems and make them work is what makes engineers tick, and that includes me.
So Vint, what are some of the problems that you're currently trying to solve?
Well, there's some really interesting ones. You see the headlines all over the place. I used to run around saying that the headline I was most worried about was 100,000 refrigerators take over Bank of America. and I used to think, haha, isn't that funny? Well, it isn't funny anymore. Those of you who follow this stuff have heard about the Mirai virus, and the botnet herder took over 500,000 webcams. Now, those webcams produced roughly a megabit per second video stream. They were unprotected. Some of them had well-known usernames and passwords to reach the device and control it, or had nothing, Just if you could find the internet address, you could take over the device and tell it, send your video stream over there. And so 500,000 of these machines sent their megabit per second video streams to one target. That's 500 gigabits a second of traffic hit the Dyn Corporation and knocked it over. That had a cascade effect because DynCorp was doing domain name resolution for a whole lot of companies. So a whole bunch of companies sort of disappeared off the net during the course of that denial of service attack. So we have the problem of devices that are vulnerable to being taken over or invaded by the bad guys. And that, there are lots of angles on this. There's improved operating system resistance to attack. I even tried to get Google to change the name of our operating system from Android to Paranoid. The marketing people didn't like that idea. But I wanted to get across the point that you have to have operating systems that are basically paranoid about the possibility of being attacked and vulnerable. So we have a lot of work to do there. We have, even those of us sitting in the room right now actually have a role to play in making the network more secure. If you're just using usernames and passwords, you are at great risk, partly because people don't pick passwords very well. Some people still use password as their password because that's easy to remember. The trouble is the bad guys know that, and they try this stuff out. There are dictionary attacks and a variety of other things. So two-factor authentication is a technology which I use, I'm required to use at Google, because we don't want just username and password to be enough to get you in. So you have this second device. That's why they call it two-factor authentication. You have a username and a password and this other device, and it generates a random additional password. But if you don't have the little device to do that, then you can't get in, and neither can the other guy. And if the other guy has the device but he doesn't have your username and password, then he can't get in or she can't get in either. So two-factor authentication is a great way of reinforcing access control. So I would love to see more and more of that happen. I have to tell you, just to give you an example of how engineers think, though, as much as I am committed to two-factor authentication and carry devices to help me do it, I have 300 accounts, across the internet. And I was thinking, you have these little dongles that, well, I'll mess up my microphone if I take that out of my pocket. No, okay, anyway, I have, my Google Badges also has a little dongle on it that has near-field connectivity and Bluetooth, and I have to push a little button at the point where I'm logging in to supply the cryptographic additional password. And I got to thinking, if I had 300 accounts, I'd have 300 of those damn dongles, and I'd be carrying this big bag. So that doesn't sound very attractive. So that means that we really have to think about, how do I build a single device that's capable of holding 300 cryptographic passwords or 300 cryptographic algorithms for all 300 of those accounts. So there's an example of a design challenge, a scaling challenge. But that's what we have to do in order to give people the safety that two-factor authentication would get. So that's, the Internet of Things is a huge challenge. It's not just two-factor authentication. It's how good is the operating system in that device? How is that device going to be updated when you find bugs in the software, which you're almost certain to find? How does the device know when it downloads a new software package that it came from the right place, that it's not a hacker, or that the code hasn't been altered in transit on the way? In an automated house, you have to think about, how do you configure all those devices? Nobody wants to sit there typing IPv6 addresses for a week. How do you deal with the fact that the people in the house have different responsibilities and authorities? So the parents should have more authority over the house than the kids, although, to be honest with you, in today's world, the kids probably know how to get around almost anything. But what if you have guests that come to the house? How do you introduce them to the house so they can use the house and turn the lights off and on and flush the toilet or whatever else? How long does that take? If it's a voice interface, do you have to have them recite to the house a bunch of words so that their voices are recognized? Do you have to issue them a dongle that they have to go around the house to unlock the doors? I mean, it's not clear how any of these things are going to work, and I'm very much focused on that. And just because I should try to answer your question with a couple of other teasers, the two other things that I'm working on are the interplanetary extension of the internet, which is now in operation, and an interspecies internet to explore the possibility of non-human intelligent species interacting with each other through the network.
Tell me a little bit more about this interplanetary internet. And what's the concept behind that?
So some of you will remember that in 1997, the Pathfinder robot landed on Mars. And it was the first successful landing in something like 20 years or so, because the previous landing of the Viking was 76. And so in 97, the Pathfinder arrives. And of course, we're all very excited about it. I was at the Jet Propulsion Lab with the team that worked on this. And we were looking at each other saying, boy, that was cool. And then we started thinking, gosh, all of our missions up until that time had used point-to-point radio links for control and for data retrieval. And we thought, boy, that seems so limiting. What if we had a network like the internet that worked all the way across the solar system? Then you could support manned and robotic space exploration far more readily than you can by just having these point-to-point dedicated links. So we, sitting around the table, said, okay, what if we wanted to build an interplanetary internet? What would that look like? So we started out thinking, well, we got TCP/IP and it works on Earth, so it ought to work on Mars. And then we started doing the math. It would work on Mars. The problem is the distances between the planets is big and variable. So just use Mars as an example. When we're closest together in our orbits, we're 35 million miles apart. So if you do the math, light is 186,000 miles a second, which is too slow. And it's at least 3.5 minutes to Mars and then 3.5 minutes back when we're closest together. When we're farthest apart, we're 235 million miles apart. That's 20 minutes one way, 40 minutes round trip. I can tell you that the TCP protocol was not designed with a 40-minute round trip time in mind. Flow control is very simple. You basically say, I'm running out of room, and the other guy says, okay, I'll stop sending until you tell me you got some more room left. Well, if it takes 20 minutes for the other guy to hear that you don't have any room left, the packets are still flowing for 20 minutes, and they're falling on the floor, and the dog eats them, or whatever happens. So that didn't work. Then we ran into this other problem. It's called celestial motion. The planets are rotating, and we don't know how to stop that. So if you're talking to something on the surface of the planet and the planet's rotating, eventually you can't talk to it anymore until it comes back around, just like a satellite. So we have variably delayed and disrupted communication in space. So we said, okay, new protocols. So we designed a new suite of protocols we call the bundle protocols, because that sort of sounds like packet. And they are delay and disruption tolerant. So we went through 4 iterations of that design from 1998 to 2004. Then the 2 rovers, Spirit and Opportunity, landed in January on Mars. And they were designed originally to transmit their data back to Earth on a point-to-point link to the Deep Space Network. These are 70-meter dishes in Canberra, Australia, in Madrid, Spain, and Goldstone, California, that were developed in 1964 to support our space program. So the rovers were supposed to transmit data back from the surface of Mars at 28.5 kilobits a second. And of course, the scientists were all grumpy about that. And then the radios overheated. And so we said, we don't want them to damage the equipment on the spacecraft, so we're going to back off on the duty cycle to keep them from damaging either themselves or the other instruments. Now the scientists are hopping mad. Then somebody else says, wait a minute, there's an X-band radio on the rovers. Yeah. And he says, well, there's also an X-band radio on the orbiters that had been sent ahead of time to map the surface of Mars to figure out where the rover should go. But they'd finished their job, but they're up there in orbit. They have power, communications, and computing capability. We reprogrammed them and the rovers so the rovers would hang on to their data until an orbiter got overhead, and it would squirt the data up to the rover at 128 kilobits a second, because it wasn't very far away compared to going all the way back to Earth. So we had 4 times as much data rate. And then the orbiter would hang on to the data until it got to the right place in its orbit to transmit data back to the Deep Space Net, which it could do at 128 kilobits a second because it had bigger antennas and more solar power, and it was outside of the atmosphere on Mars. So we built a store and forward network using the prototype implementations of the interplanetary protocols. So all the data that's come back from Mars, from those rovers, including the Mars Science Laboratory, has come back through this store and forward network. Meanwhile, we've perfected the interplanetary protocols. We've standardized them with the Consultative Committee on Space Data Systems, which is a UN organization made up of all the spacefaring nations. So now that's standard. It's available as source code on GitHub. It is now running on the International Space Station. So now we have a 2-planet and 1 International Space Station network that we can use to test the protocols. The plan now is that a deployment plan is now in development so that all the spacecraft that NASA produces and the other spacefaring nations, if they wish, will carry these onboard protocols. Now, even if they don't use them for their primary mission, when they finish their primary scientific mission, they could be repurposed as nodes of an interplanetary backbone. And so as the missions are launched in the subsequent decades of the 21st century, we'll literally accrete an interplanetary backbone over time. So by the time 2050 or 2060 rolls around, we'll have a backbone network that we can rely on for both manned and robotic space exploration.
That sounds...
What's not to like about that? I mean, it's cool. And actually, it doesn't even stop there. The next piece is the mission to Alpha Centauri. And now this is a tough one, right? Because Alpha Centauri is 4.3 light years away. And with current propulsion systems, it takes 74,000 years to get there. That's kind of a long experiment. And that's 7 times longer than our civilization has existed on this planet. So the first problem is, can we get there in 100 years? Can we actually develop a propulsion system that will get us up to maybe 10 to 15 or 20% the speed of light? And there may be some ion accelerators that will get us to that speed. Remember, they have to go for 50 years to get halfway there. Then they have to flip over and slow down, because otherwise you'll go blasting through Alpha Centauri at 20% the speed of light and get 1 picture if you're lucky. So we have to slow down and go into orbit. So it may be that an ion engine will do the job. So that's the propulsion problem. Then there's the navigation problem. You know, normally when we do a space mission in interplanetary space, somewhere halfway through the mission we do mid-course corrections. And it's not too difficult. I mean, it takes minutes to hours to send the mid-course correction data and get a response back. But that's, you know, that's reasonable. Imagine that you have a spacecraft on the way to Alpha Centauri and it's a light year away. It's going to take a year to send the signal to say you should change your course a little, and it's going to take another year to find out what happened. This is not exactly interactive. So we're going to have to do what is called onboard independent autonomous navigation. Fortunately, there's a way to do that. You know, everybody here uses GPS, right? That's because we got all these satellites around Earth and they help us figure out where we are. It turns out that there are stars in our galaxy that are flashing, and those stars are very, very reliable. The galaxy is not moving rapidly, so that they're more or less in the same place and will be for quite a long time. And so we can use those as navigational aids. So we can do independent navigation to Alpha Centauri without having to send mid-course corrections. So that takes care of navigation. Then comes communication. You're 4.3 light years from Earth. How the hell do you generate a signal that you can actually detect from 4.3 light years away? And so at the moment, I'm favoring things like femtosecond or attosecond lasers, or 10 to the minus 18 second pulse lasers. If you got 100 watts of power and you compress it down to 10 to the minus 18 seconds, that's a big spike. And so that, you know, if you could transmit a pulse laser back towards Earth, you should be able to detect that signal, except for one problem. Even a laser is going to beam spread over 4.3 light years. So now the problem is, how in the heck do you pick up that signal? It's now very dispersed. That's why I need the interplanetary backbone, so I can build synthetic aperture receivers to reintegrate the signal coming from Alpha Centauri.
Sounds like a thorny problem.
So that, you know, you can just see, look, this thing is, I won't be alive when all this actually happens, but it doesn't matter. When you get to think about this stuff and try to work out the solutions to the problems, it's like being part of a science fiction story. So I'm happy as a clam knowing that even maybe 100 years from now, this mission will actually succeed.
So, Vint, I want to throw it to the audience in a bit, but before I do, I want to ask you one more question. We've seen a lot of headlines, as you sort of alluded to lately, about how the tech industry is handling people's data, whether people have enough privacy, whether or not there should be more regulations placed on the tech industry and its practices. What's your take on all that?
So privacy is really hard to come by in our society. When you think of all the people like you running around with your mobiles, you can take pictures, you can upload them to the net without thinking much about the consequences to other people. Forget about what information you may have put up yourself. By the way, and this is not an argument against imposing responsibility on companies to protect people's information, but it's the fact that we can interfere with each other without realizing it that is so rattling. So imagine that, Brian, let's pick on you. So you're in Cairo, and you're standing in front of the pyramids, and you ask somebody to take a picture of you. And so you hand your camera to somebody, and they take a picture. And so it turns out that that not only do they get you in the picture, but they get me in the picture too. Now, you don't know me, and I don't know you, and I don't really know that I'm in the picture. But you post this thing on the net because you were kind of proud of being in front of the pyramids in Cairo. And let's suppose it's June, this year. Well, somebody is searching the net for pictures of pyramids, and they find this picture of you and me in front of the pyramids, and it has a date on it. It says June, 2018. But this person knows who I am and thinks, hey, Vince in Cairo in June, he told me he was going to be in London. So now I'm in trouble because you asked somebody to take a picture of you and you happen to catch me in the picture. So it's these scenarios that should also kind of bother us, and I'm not sure what to do about it because I don't think we can ask permission from everybody who happens to get caught in a picture. But we can certainly do a lot more to protect the information that companies accumulate in the normal course of their business. That's why the telephone companies are told that there is information about your telephone calls that is considered, must be protected, that it's private information. So companies like Google and Facebook and Yahoo and Amazon and others who normally accumulate a lot of information about their customers in the normal course of business have an obligation to protect that information and not allow it to be either stolen or certainly not handed out and make a business out of sharing, let's say data brokers, sharing the data. I think that's an obligation that we should all feel strongly.
Do you think there could be a business model built around a system where consumers control their data and are able to revoke it?
It sounds attractive on the surface. This is one of those, on the surface it's profound, but deep down it's shallow. The problem is complexity. After a while, you would go nuts trying to cope with every request that's made to share a piece of information, and even getting enough information to figure out what is it that they wanted to do with it. We would probably become very frustrated very quickly. So it's very tempting to try to invent an idea that would do that. Probably the better thing is to have a clear understanding ahead of time before you engage at all with what information is going to be accumulated and what will be done with it. And I think that transparency and clarity is important. So you can make a decision, do I want to have this data used for anything or not? Mm-hmm. And just at Google, there are some people who imagine that Google's business model is to accumulate a bunch of data about users and then sell it. And we don't do that. What we do, it's true that we kind of look for patterns, and we even tell you about which patterns we're discovering, and you can erase some of them if you want. But we just look for patterns. We don't really care who you are. We just care about the patterns you make. So when you do a Google search, for example, while we're trying to get the answer to the Google search, we're also over here in this grab bag full of 1 billion ads, and we're pulling one out, some out, saying, these look like they are responsive to what you were searching for. And then we try to rank order those and put them up in the hope that they'll be significant to you. The advertiser doesn't get paid unless you click on the ad. So that's fair, because the advertiser doesn't spend money unnecessarily. But we never share the information with anybody. It stays inside Google, which is where it belongs.
Let's take some audience questions. I'm sure there are a lot of them. Please wait until the mic reaches you. We have a mic.
There should be a roving microphone somewhere.
And so if you have a question, please raise your hand.
Hands up.
Send you the mic.
If you don't have any questions, we're going to keep talking. Here's 2 questions.
I've got a load of questions, so if no one wants to talk, I'm totally fine with that.
Thank you for being here this evening. You've spoken and written about the concept of bit rot and the persistence of data over time. Have you been working on that problem recently, and what are your thoughts on it?
Yes, I have. So here's I hope I scare the bejabbers out of everybody here. You all take pictures with your mobiles. You probably have them not only in the mobile, but you put them up in the cloud, and you sort of feel like they're always there and they'll be there forever. Well, maybe not. You'd ask some questions at the beginning, or you asked the questions at the beginning, right? Okay, I got a question. How many people here know what a 5 1/4 inch floppy disk is? Look at that. Have you got them in your closet? Do you have any readers for them? Yeah, there's one. Okay, I believe you. Or a 3 1/2 inch floppy disk. I mean, the problem is that the digital media have finite lifetime, either because the medium itself goes away or because you can't find a reader to read it, even if you, and it gets worse. Suppose I have an example. I bought a 3 1/2 inch floppy disk reader on eBay.
How much did that cost?
Oh, not much at all. I mean, like, I don't know, $20 or something. eBay, used, you know.
Not like an antique item at this point?
For $20, you know. Anyway, it was a USB thing, so I plugged it into my current Macintosh, and I stuck in a 3 1/2 inch floppy disk, and I pulled up a bunch of files. It was great. It was my wife's cookbook in WordPerfect. And I didn't have a WordPerfect that was running in my modern Macintosh with its current OS 10, whatever it was. So this is the other problem. It's that the bits have meaning sometimes because there's a piece of software that knows what those bits mean, just like the end-to-end thing in the internet. And if you can't run that software anymore, those bits may not be useful to you, which is why we think of them as rotten bits. So the question is what to do. There are 3 pieces to the answer. Answer number 1 is we have to find a way to preserve data over long periods of time, which almost certainly means copying the data from one medium to another over time. Second, we have to find a way to preserve the software that's needed to interpret the bits, if indeed that's necessary, which most of the time it will be, even for images. And so we now have the technical problem of capturing that software and either capturing source code, which we can recompile on new platforms, or emulate the old platforms and run the old operating systems that ran the old applications so we can interpret the bits. Then you get into these legal questions, like who has the right to run the intellectual property, the code which is proprietary, and when are they allowed to do that? I mean, suppose I'm a data archive. I offer this as a service, and you have these old files that require WordPerfect to run. Am I allowed to run a copy of WordPerfect on an emulated machine in the cloud or not? Depends on what the intellectual property terms are, and whether the software is protected by patent, for example, for some period of time. So we have to resolve that, and it might mean, for example, that we would give to a data archive privileges to run software that we might not grant to others. This might be the same argument as evolved out of copyright when dry copying came along, when Xerox came along. The fair use doctrine emerged out of the debate about what you were allowed to copy and what you were not allowed to. So we have those technical and legal things to resolve. Then there's a business question. What's the right model to pay for long-term storage? And if we're talking about 100 to 500 years, It's a very interesting question. What organizations last that long? And there are a few that come to mind. Libraries, universities, breweries and wineries, and the Catholic Church, which incidentally had something to do with the preservation of data during the Middle Ages when they had monks copying things from one manuscript to another vellum manuscript. So figuring out whether any of those entities could become the basis for preserving data, the business basis for preserving data over long periods, is an open question. But I am pursuing this because I'm very worried that the 22nd century is going to have no idea what the 21st century was like if we haven't been able to preserve our email and our blogs and our tweets and our, of course, maybe they don't want to know about those tweets anyway, yes, the short answer is, yep, I'm still working on this problem. But you can see that's the complexity and the challenges associated with it.
Let's take another question. How about in the back, the red jacket?
Back to your commentary on the security dongle, could you see a scenario in which there's a 3-factor authentication with that sort of device where the user uses a thumbprint and then the security dongle has a sort of OCR or GUI recognition of you could scan the website that you're logging into, and then there's a encryption code that goes back and forth between the two?
So, in fact, there exists some things like that today. I mean, you can buy a mobile or a laptop that does fingerprint recognition, for example. I tend to be very cautious, though, about bio identification. And the reason for this is roughly the following. If someone manages to capture your fingerprint, you can't cut off your thumb or replace it or something, just like your eyes. So you want to be careful not to use a purely biological identifier if you can mix it with something else that the other party doesn't have, which is why the cryptographically generated string plus your eye pattern or your thumbprint or something would be a better design point than just the biomarker. There's also a technical issue here. What happens when you do a fingerprint scan is that the scan is reduced down into a smaller size set of bits. A hash code is done or some other compression algorithm is run. If someone is able to inject into the system the bits that are needed to make it look like your thumbprint by electronically finding a way into the system past the scanner, after the analog to digital conversion is done. If they can find a way in, then they can pretend to be you, particularly if all you have is a fingerprint scan or an eye scan. So if you have, in addition, this second factor, then you can stymie even that kind of an attack. So I am not comfortable personally with a purely bio identification. Now, having said all that, I confess to you, I use the Clear system at the airport, and it uses my two-finger fingerprint thing. But it's also bound together with a ticket and a bunch of other identifying things, including my driver's license or my passport, have been examined before they issue the boarding pass. So I'm not entirely dependent solely on the biomarker in this case. The other things also have to have happened. So that makes me feel a little bit better. But to be frank, when I have an account at Barclays Bank in the UK, and when you get the account, they issue you this little card reader that reads the chip in your credit card, and it generates a cryptographic identity for you to log into the system. And then when you do a transaction, they encrypt the transaction, digitally sign it with the destination account number and the amount. So that by digitally signing that, nobody can change the account destination or the amount destination as it's going through the system because it's been digitally signed. So I actually don't mind carrying that little dongle around with me because it feels better and safer than I am without it. But once again, that's only 2 out of 300. So I still think we need to invent that other gadget. Okay.
Let's go here in the middle, the check shirt.
Thank you. In yet more proof that the universe has a sense of humor,
You know why? It's the last name that does it. For some of you, remember Vint Cerf and What's My Line and Random House and all that. People ask me if I'm related to Bennett, and the answer is I'm his father. And it's actually true. Our youngest son's name is Bennett Christopher Cerf.
Thank you. That was not my question, but it should have been.
But
the sense of humor I had in mind was that it would appear subjectively that the first really publicly, easily understood and acceptable manifestation of artificial intelligence in society is just about ready for prime time, autonomous driving, in the 50th anniversary year of 2001, A Space Odyssey, and HAL, the computer. How do you think about AI and its implications for society as a whole, and as a policy guy specifically? How would you recommend getting policymakers not to be so scared that they kill lots of potential AI-generated golden geese?
Out of concern that the AI is going to kill a lot of people, for example. I mean, that's right. I'm sorry, I can't let you do that, Dave, if everybody remembers the quote. So a couple of things. First of all, artificial intelligence is still has its little places where it goes clunk. And so we all need to be conscious of that. At the same time, most of the artificial intelligence that you see today is really better called machine learning. And it's driven by multi-layer neural networks. The neural network idea is not new. It was explored in the 1960s, but it was sort of one layer deep. And so it had very, very little capability. The ability to build a 100-layer or 500-layer neural network and to make it work in almost real time is a dramatic shift. I like to tell a story about our early experiments at Stanford University in the 60s in artificial intelligence and natural language translation. We thought it was sort of straightforward. You just put a dictionary in the computer and you run it. And so we put an English-Russian dictionary in the computer, and then we typed in out of sight, out of mind. And we translated it into Russian, and then we translated it back into English, and it came back invisible idiot. And then we realized there was more to this translation than just putting the dictionary in. So there's been a number of cycles since then, but the machine learning tools with multi-layer neural networks have dramatically improved our ability to do natural language translation. So first of all, I have to give credit to Senator Warner, who has a bill which is focused on the Internet of Things at the moment, but it's a similar kind of character. I think he and others recognize that these processes are mostly augmenting our own ability to think. I mean, when you do a Google search, you're putting a huge amount of processing together, including some AI or machine learning tools. Our knowledge graph, for example, uses semantics to help figure out how to expand the search of the World Wide Web Index in order to return more useful results than just the terms that you used. Machine translation is also using these same machine learning methods. So the first step, I think, is to explain, if anyone will listen, how this stuff works, what its strengths and weaknesses are. I think Eric Schmidt and I and others at Google see this as tools that we can use to augment our own capabilities, to do things faster that we couldn't do on our own. And so I don't see them as things to be feared. The thing I actually worry about more is not AI and not machine learning. It's autonomous software. In other words, it's software that we just give control to and step back, which includes the self-driving car. And so the thing I'm most worried about is software that has not been given enough thought and testing that we then trust with our safety and our lives. And I have to say, having looked at what the Waymo guys have done in terms of testing, that they are light years ahead of what the current federal guidelines are in terms of the degree of testing that they do. And I realize I'm chewing up a lot of time. I'll try to make this part short, but it's very impressive. They have driven, the cars have driven on the order of 4 million miles in city traffic in San Francisco and in other cities, plus there's an abandoned Air Force base that we turned into a little experimental village to try out new algorithms. But the more important thing is that all the sensors of the car get data and turn it from analog to digital data. So eventually the sensor information gets to the software in the form of digital measurements. We can emulate that. We can create scenarios that would not be easy to create in the real world, but we can invent them in the virtual world, and we can feed that data to the same programs that would be getting the data from the sensors. We've driven 2.5 billion miles in virtual space on these cars. And so that means that when we're about to release a new piece of code, we can drive the cars in simulation with the same sensor data they would have gotten if they were actually out on the street. And we can do things that we would not do in the real world, like have the ball roll out and a little 3-year-old run after it and see if the car stops or not. We can emulate that and see if our software continues to do the right thing. So the interesting thing is every time you have a new release, you can test that release against a whole variety of edge cases. And even better, you can do it in parallel. Because since it's emulation, you can have 1,000 cars all being exposed to different scenarios at the same time. So you can get this done in a hurry if you have enough computing power. And we got a lot of that. So, you know, so actually, just in terms of self-driving cars, I am pretty confident that if you design around this kind of testing framework, that you have a pretty good chance of doing a good and safe job. The other thing that I am very attracted to in the case of the self-driving car compared to the distracted humans that we have behind the wheel is that the cars can see 360 degrees around them. Now, we all know about that tragic accident in Arizona, and I don't know anything more than what we've all read in the newspaper. I have come away with the impression that maybe they didn't have as many sensors as they might have had. I think we have said publicly we think that the Waymo car would have detected this woman crossing the street. But it's just another good example of why it's so important to test this to a fairly well before you actually let anybody get in the car and drive in it.
So we got time for one more, I think. Let's go on this side in the back.
We have a reception.
There's a reception after.
Yeah, there's a reception, and I'll be here, so we can keep going if you like. Okay.
Could you please talk a little more about the cryptocurrency and blockchain, and what are the biggest disadvantages of it becoming a lot more popular or acceptable?
I'm sorry, was this the blockchain question?
Crypto and blockchain.
Crypto blockchains, yeah. That's question number 103.
The first that was one of my questions, so thank you for asking.
Yeah, well, the first question 101 is, did you have any idea this network was going to get this big? When you were, okay, so blockchain. Thank you for asking about blockchain and not Bitcoin, because the Bitcoin answer is run away. There are a lot of people who are really excited about Bitcoin or other cryptocurrencies, initial crypto offerings or coin offerings and things like that. They don't have any intrinsic value. But let's talk about blockchain, because it's basically a distributed ledger, and that has some nice properties. Multiple parties have copies of the same thing. It's hard for somebody to fabricate an instance of a block in the ledger without everybody else noticing it. But there are some factors in the current blockchain implementations that make it applicable for some, usefully applicable for some cases and not so useful for others. The first problem is that when you form the next block, remember this is essentially taking a bunch of transactions and drawing a box around them, calling them a block, and then having one party in the distributed system digitally sign this block of new data and bind it digitally with the previous block. So now you form a chain. And the theory behind this binding of the new block with the previous one is that in order to change anything in any of the blocks, you'd have to keep going back, changing everything until you could get the digital signature to look right. So it's very hard to inject false data into the system unless, of course, you happen to be the guy signing the block. And you could change everything if you wanted to and then sign the block. But then everybody else would notice, in theory, because what you signed would not be the same as what everybody else had, waiting for the next person to sign the next block. So then the problem is, who signs the next block? Because it can only be one party. If two parties sign the block with different signatures, now you bifurcated the chain and nobody knows which of the two blocks they should be using to build up the next chain. So you have to have a consensus algorithm to decide who signs the next block. That can take time, especially if it's a highly distributed blockchain. There are also variations on this. One of them is the anonymous blockchain, where you have no idea who's participating in this system. You don't know how many of them there are. I am not comfortable with that because I don't know that I can trust every possible signer of the block. I like the permissioned blockchain, where I actually know who the parties are that are maintaining the distributed ledger. Then I can at least say, do I trust these people to manage the thing? So the rate at which you can generate blocks can affect the kinds of things that you can record usefully. So if you're doing 1 billion transactions a day in a transaction system, it's not clear whether blockchain can keep up. So there are variations on blockchain. There are hierarchical structures that try to deal with the speed with which you can record transactions. I would say that a lot of people have fallen in love with blockchain without admitting that there are other ways to do the same thing that might be more efficient or just as efficient, especially if you want to compare a permissioned blockchain with a more conventional distributed database. So I don't think that this is going to be a panacea. It does have some convenient properties. We use blockchains inside of Google for certain applications too, but they're sized in a way that makes sense for blockchain algorithms. So I would be cautious about betting too heavily on blockchain. I think it's going to turn out to be a useful technology, but I don't think that it's the hyperbolic thing that a lot of people have made it out to be. I'd be interested to know whether the Patent Office has an opinion about this, but we'll have a drink over up there.
That's one for the reception.
Talk about that, yeah.
Well, unfortunately, that's all the time we have for this part of the agenda. But thank you, everyone, for joining us, and thank you, Vint, for.
Thank you.
Well, thanks all of you for coming. Just a couple thank yous here, and then I'll let you guys go eat. Thank you to Dean Otter and the Georgetown School of Continuing Studies, providing really a wonderful venue here, as well as helping us put on this AEW. Thank you to the Director Iancu and the United States Patent and Trademark Office for their support. We really appreciate it. Couldn't have done it without you guys. Most importantly, thank you to Vint for doing another incredible job, for another informative AEW. Brian, also wonderful job. Thanks a lot. Let's give them both another big hand. All right. We have 5 more AEWs this year. If you want to find out how to view them or come to them, go to our website, nationalmetals.org. We live stream all of our events, so if you can't make it in person, please tune in. We have some fantastic people we're going to be featuring, and they've all got great stories to tell. Okay, so please go eat. It's upstairs. There's some good food. Continue your conversations. It's a really great time to continue that process. If you have any questions about our foundation, please feel free to come talk to me. You can talk to Laura. She's in the back over there with her hand raised. Allison as well. Vint is also a board member. He can answer questions as well. Also, finally, I think there's some T-shirts left, swag left. Please take them with you. We were trying to get rid of all this stuff, and it's free. So who doesn't love free stuff? So thanks again for coming, and have a great night.